FDP is AI and cybersecurity in the digital era, LLM, generative AI, e-commerce analytics, and federated systems. So this is the core concept of this FDP. Here I would like to thank our management, higher officials, Vice Chancellor, Vice Chancellor, Registrar Sir, Principal Sir, Head of the Department, Kalpana Ma'am. I welcome all the dignitaries to this wonderful evening, a wonderful FDP. And I would like to invite all the participants from the various parts of India and the students from different parts of India and different colleges. It's my great pleasure, and I would like to welcome the resource person of today, Manu Madhavan sir. So here, this FDP, the idea behind this FDP is to share the latest technology and related information to all the community who are joined in this FDP. So once again, I welcome all the participants, the dignitaries who are gathered here. Sir, Manu Madhavan sir, welcome sir. So once again, welcome all the participants, and I would like to request to make use of this FTP, the points, the various important points from the various resource person. Thank you all.
Thank you, sir. Good afternoon, good evening to one and all present here. This is Dr. R. Kalpana, Head of the Department, CSEAI, MITS DIM to be University. First of all, my sincere thanks to our management, who is always encouraging us to conduct such events for the benefit of faculty and student members. I thank our Vice Chancellor, sir, Register, sir, and Principal, sir, and VP, sir, for always motivating us to conduct such events. I thank today's 6 days FDP coordinator, Dr. Chokanathan, sir, and Dr. Vamsi, sir, and Mr. Muhammad, sir, for organizing such wonderful FDP. I thank today's resource person, Dr. Manu Madhavan, Triple IT Kottayam, and coming days, Dr. B. Surendran, Jerry, and Dr. Ramasamy, Vidyabhyam University, Bengaluru, and Dr. G. N. Vivekananda, VIT Vellore, and Dr. Wenningston, NIT Srinagar. This is 6 days FDP online FDP program will be very useful for our engineering faculty. This is a thrust area in this era, and AI and cybersecurity, that is a very common and the latest topic. So that's why we have chosen this topic. This FDP is sponsored by IEEE Robotics and Automation Society. Today, our chief guest, resource person, Dr. Manu Madhavan, is going to take the session on introduction to LLMs. Sir, welcome you, sir, Manu Madhavan, sir. And I request all the, thanks for all the participants for registering in our FDP. And I hope these 6 days will give the enrichment in these AI and cybersecurity test areas. Now I request our principal, sir, to give his address to this FDP. Thank you, sir.
Yeah, thank you, madam. Am I audible?
Yes, sir, you are audible, sir.
Yes, sir, you are audible.
Audible.
Yeah, a pleasant evening to one and all gathered in this online platform. Respected HOD of CSEAI department, Dr. Kalpana madam, coordinator for the program, Dr. Choknathan sir, Dr. Vamshi sir, other faculty colleagues of AI department, participants from other colleges, students from other colleges and our own college. It gives me immense pleasure to be in this online forum to initiate the FDP, which is being organized by the Department of CSEAI. I think whatever topics they have mentioned are emerging areas, and a lot of scope is there for doing research. In that direction only, faculty development programs are conducted to improve the caliber of teaching, learning for the students, as well as to promote the teachers to learn new technologies from eminent resource personalities. Many eminent resource persons have readily accepted our invitation to deliver the talk in this FDP. In this direction, I congratulate and appreciate all the eminent resource personalities for sparing their valuable time and effort for the benefit of this FDP. And I hope the faculty members and students and the other participants will utilize this in a good manner and get benefited. Also, it is my heartfelt congratulations to the entire team of CSCAI for organizing this FDP. I thank the organizers also for inviting me to be a part of this occasion and address the online forum. Thank you for the opportunity being presented.
Thank you, sir. Thank you
sir.
very much for your inspiring speech. Now I request Dr. Pradeep sir, register MITS deemed to be university, to address the gathering.
Yeah, thank you, ma'am. Good evening, one and all. First of all, I congratulate the Department of Computer Science and Engineering Artificial Intelligence for coming forward to organize this 6-day online faculty development program on AI and cybersecurity in the digital era. LLMs, generative AI, e-commerce analytics, and federated systems. These days, we hear that there are many activities, many areas, many fields, many industries being affected by the significant growth of artificial intelligence into every arena. So catching up that speed and momentum. So our AI department also is organizing this faculty development program. So it is once told that students who are studying AI, by the time they complete their course, 2-year, 3-year, or 4-year course in AI, by the time they complete, probably the courses that they have studied have become obsolete. If that is the case, what about the faculty also? Faculty who are teaching a particular subject, after every 2 years, they have got to upgrade themselves to new technologies, new advances that are happening in the field. So in that connection, I appreciate the Department of CSE AI to come forward this faculty development program. Not only now, I think the very nature of Department of AI is that they need to be conducting such programs more and more frequently, so that all the faculty, not only of MITs, in faculty from other institutions also, and also the students should upgrade their technologies and advances in these areas. I congratulate all the faculty who are attending this, especially even the faculty from outside the institution, from other engineering colleges, other institutions, and the students also. I wish all the faculty and the students best of luck, happy learning. So from our management, Dr. N. Vijayabhaskar Chaudhary Garu, Chancellor, Vice Chancellor Dr. C. Yuvraj Garu, and all the other management members, I congratulate and thank the Department of Computer Science and Engineering Artificial Intelligence for organizing this particular program. All the very best, happy learning for all the 6 days. Thank you very much. Thank you, one and all. Thank you.
Thank you, sir. Sarisha, sir, thank you so much, sir. Next, I would like to request Dr. Ramsey, sir, to read the profile of today's resource person, Manu Madhavan, sir. Sir.
Thank you, sir, for the opportunity. Good evening to all the participants. It's my great pleasure to introduce today's resource person. We are honored to have Dr. Manu Madhavan, sir, from IIIT Kottayam with us today. Dr. Manu Madhavan will be delivering a session on Introduction to Large Language Models. His insights into LLMs and their applications will lay a strong foundation for the sessions that follow. Dr. Manu Madhavan, sir, is an assistant professor in the Department of Computer Science and Engineering at the Indian Institute of Information Technology, Kottayam, Kerala. He holds a PhD in bioinformatics and machine learning, and has a strong academic and research expertise in natural language processing, machine learning, deep learning, and computational linguistics. His work spans AI applications in language technologies, semantic representation, and applied machine learning research. We are honored to welcome Dr. Manu Madhavan, sir, to our FDP. His expert insights in AI and advanced language models will greatly enrich our learning experience. I now hand over the session to you, sir. Over to you.
Thank you. I hope I am audible. Am I audible?
Yes, sir, you're audible. Sir.
Yeah, thank you. Thank you. So let me share the screen. Is my screen visible?
Yes, sir, visible, sir.
Okay. So very good evening all, and thank you for this opportunity. Thank you for the introduction, and congratulations all the team for this wonderful, uh, like wonderful FTP team and wonderful topics. So on this first day, my duty or my plan is to discuss on what is large language models. So we will discuss majorly the background or the evolution of technologies, especially the NLP technologies, from a rule-based to the current large language model. So we'll discuss what is language model in essence. Then we will talk about other the evolution of language models from rule-based chatbots to statistical models to neural language models to current large language models. Then we will discuss the key component of this large language model, which is transformers. So we'll talk about transformer architecture, not in depth, but not very briefly. We'll talk about the large like we talk about transformer, and we'll see how this transformer architecture lay a foundational model in all these large language models, like how a transformer become a large language model, what kind of training process are happening, what kind of other activities are happening in large language models. Then we'll see some examples how a traditional application of traditional neural language model or a traditional NLP application now turned into a large language application. How a pre-trained models can be used, how it is efficient, how effective it is. And finally, we'll think about the concerns that is also raising with the development of this kind of technologies. And finally, conclude this topic with all the summaries and some future directions. That is the plan for today. So before moving to the idea, we must know what is meant by a language model. So the key concept in natural language processing is language modeling. Before moving to language modeling, let's say natural language processing. We'll discuss transformer, language modeling, everything in the context of language, natural language processing. Now, this topic is beyond NLP, beyond text processing. We can see LLM applications in many other fields also, like images. We have vision transformers, we have video transformers, we have text related transformers, we have transformer for many other areas also. But our discussion is strictly focusing on language related activities of this large language models. So let's understand what is NLP first. Natural language processing is an area of artificial intelligence which tries to process natural language, that is, the natural language or languages used by human to communicate, not a programming language, not a structured language, not a definitive language. It is natural, as the name indicates, versus the artificial language. Like if you take a Python program, this is basically an artificial language, a synthetic language, have a very finite set of grammars and rules. Or if you see some coded language, like for defense and all, they may make some codes, like this word corresponds to this sentence, this word corresponds to secret codes. So that coded language is also not natural. They are strictly artificial languages. But here NLP, we are talking about natural languages which are naturally used by human to communicate. Like for example, Hindi, Tamil, Malayalam, English. All these languages are evolved with respect to human evolution. They are not very strict. Though we have some grammars, they are not strictly following the grammar. There are many other factors that contribute to the communication. For example, we can see when we are communicating, we are not strictly following the grammars, but we are adding some kind of say silences or some kind of jargon, some kind of like hummings to make the communication more effective. So that is natural. So whether the machine can be natural, that is the question. And how to teach this language to computers, that is one problem. So people are talking about a concept called language models. So language modeling is the key concept in computer program like natural language processing. So what our objective is, we want to represent these languages. We want to represent, 1 minute. Yeah, okay. So we want to represent a sequence so that computers can understand the sequence, because natural language is a sequence of tokens, sequence of words. So how a computer can understand the meaning of a sequence and respond meaningfully to that sequence. So this is basically a sequence learning task. So natural language processing, whatever be the task, it can be a text classification, it can be a sentiment analysis, it can be a POS prediction, POS tag prediction, it can be named entity recognition, it can be summarization, it can be translation. So whatever be the task, it basically tries to learn from a sequence and respond a sequence or a one, like based on the sequence, it will have to respond. Maybe a sequence as a response or a one word as a response. So this is basically a sequence learning task. So how to teach the sequence to a model in the sense a machine, is the question, and this is basic problem in natural language processing, a sequence learning problem. So one such problem that usually used in all this computer, like one that is defined by the concept called language model. So mathematically, this process, the sequence learning process is basically language model or modeling a language. So what is meant by a language model? It is very simple. If you observe the language, the distribution of characters or distribution of words in a sentence, we can see that some kind of probability you can see. So what is probability? Probability is the modeling of uncertainty. We can find that it is not equally likely, like it is not uniformly distributed. Let's see the character distribution. Do you think, do you observe or do you know which is the most frequent letter in English? You know that all the letters are not equally distributed. The count, if you take a text, a random text from newspaper article or Wikipedia article, and if you check the count of characters, you can see that the number of characters, the frequency of characters are not equally likely, not uniform. Some characters are more frequent, some characters are very rare. For example, E is most frequent character, the most frequent alphabet in English. Maybe Z, maybe the least frequent. Vowels are more frequent than consonant. And some characters have some affinity. Suppose the first letter is Q, the next letter is probably U. So there is a kind of probability you can see, like the probability of U given Q is the previous character is very high. Q follows U is very high. Then Q follows some other characters. Or let's comes to the word. If I say I ate, the boy ate dash. Since my sentence is the boy ate dash, your probable guess will be something like apple or orange, mango. The boy ate apple. The boy ate mango. The boy ate dosa. The boy ate idli. You will not predict something like the boy ate a car. The boy ate a mountain. Why? Because you know that the ate will not follow the words like car or mountain. It is not edible. So something edible will give the more probable things. So how we know that this is most probable one? Like we are talking about our prediction. We know that this will be the most probable prediction. How the machine can understand this as most probable things. So what you can understand here is that we can model this kind of relationship using a probabilistic model. So something like prob P of I will try to write. Let me escape from this one. So what is the probability of a word 8 follows? So the probability P, we know that the probability P of some words like apple being the next word given the previous word is something like 8. This is what we are computing. So a language model tries to compute this probability. So simply a language model is given a sequence or given a set of sequences or a corpus of text, a data set of text data. So a language model tries to learn this probability of a word given the next word, or probability of what is the probability of nth word given a sequence of previous n minus 1 words, or what is the probability of n words, probability of w1 to wn given a sequence of word, what is the probability that this words form a valid sentence. So this probability will be learned by a language model. Suppose you know this probability, you can apply the chain rule and compute the corresponding probability. Not just word level, we can think about a sentence level or we can think about a character level. But we will talk about word level for the convenience. So a language model tries to predict the probability, or we can say it will predict the most probable the word. Given a sequence w1 to wn minus 1, it will predict the most probable nth word. Suppose I have 1,000 words in my vocabulary. Vocabulary is all collection of the words. It will assign a probability that this word will be the probability. This word will be the, what is the probability that this word wi being the next word given the previous n minus 1 word. So in short, this probability, sequence to sequence learning problem, we want to learn a probability from this data, or we want to learn a sequence probability. So language modeling is nothing but a model has to learn this probability, and based on this probability, we want to predict. And if you see, any of the NLP tasks can be modeled as a language modeling task. Suppose you want to predict a sentiment analysis. You want to predict which is the sentiment analysis and NLP task. You will give a movie review. You want to predict whether the sentiment of the sentence or the text is positive or negative. The movie was awesome, or Sanju Samson played well. What is the sentiment of this sentence? So it can be positive or negative. So what we can model it as, what is the probability that a positive given the word sentence is Sanju Samson played well. What is the probability that the Sanju Samson will played well gives a positive sentence, gives a negative sentence, and among these sentences, which one is maximum? That will be treated as the final output. So text classification can be a language model task. Now comes to translation. I have a sentence like he went to school, and we can relate it like as say avan school il poi in Malayalam, or any language we can take school jata gaya hai in Hindi. So what is the probability that was school gaya hai will be the output given the input sentences given to school? So any language, any NLP task that we can be represented as a sequence learning task, or in essence, we can represent as a language modeling task. So before moving to the current approach, the state of art language models, this is like there are many techniques evolved in NLP history. One such method is engram-based model. So engram-based model is basically a statistical model. We call it a statistical language models. What it assumes that, like it will use the idea of Markov assumption from statistics. What Markov assumption says, if we have a sequence of events, then the nth events output, the probability, can be approximated by a limited history. Usually we'll say we have a chain of days, like say I have the day, the weather reports of last 10 days, like today 10th day, last 10th day was rainy, second day was rainy, third day was rainy, fourth day was some sunny. Like that, all the days weather report is there. And based on this 10 day, I want to predict what will be on 11th day. So Markov model, like if you are going with first order Markov model, it says that based on the previous day, I can predict the probability of next day. Or if it is third order or second order, we'll say it depends on 2 days. Like based on 2 previous day, we can predict the next day's weather. So that is basically a Markov model. So that is basically an approximation. We are approximating the model to a particular limited window. Coming back to the language modeling task, what it says that the nth word probability can be approximated by the previous day, n minus 1. So in this case, the boy ate apple. So the next word is being apple is just depending on the previous word ate. So this is basically a bigram model. It just depends on 2 words. The probability we are computing based on two words. Like if the sentence is the boy ate apple, the bigram will be the boy ate apple, that kind of combination. This will be the bigram. So that is basically the bigram language model. You can extend to trigram, like 3 words. So the next word depends on 2 previous words. So 3 word combinations, try word. You can have 4 gram, 5 gram, 6 gram, generally n gram. So the nth word depends on previous, or n plus 1 word depends on previous n grams. It can also be unigram. That is, it just depends on the current word. Like next word is not depending on any of the previous word. Whatever be the previous word, we'll have a new word prediction. That is unigram prediction. So that is the basic idea of statistical language modeling. Given a text data, from the text data, we want to compute all the probabilities, n-gram language models, n-gram probabilities. So calculation is very simple. If you have a sentence, we can count the number of bigrams. So probability of A comma B. So what we are actually computing is probability of A given B, which is probability of A and B divided by probability of B. So we can compute all the bigram probability, how often these 2 words comes together, divided by what is the probability of the unigram. So I want to compute 8 apple, the probability of 8 apple. So how many times 8 apple coming in the sentence? The boy ate apple, the girl ate apple, she ate apple, Ram ate apple. All 8 apples will be there. So I will count the total number of 8 apple divided by how many times 8 comes in the model, in the data. So that will be the total probability of 8 apple, the bigram probability. So that is basically a statistical language model. Later that this computation, like sometimes this probability may not be available. Some pair of words may not be appear in the corpus very frequently. Sometimes it may not appear in the corpus, so the probability becomes 0. So if some probabilities are 0, we cannot compute the entire sequence probability because some entries in the chain rule will be 0. So that will be that is a problem in statistical language model. To avoid that, neural language models were introduced. Like can we use a neural network so that it can predict the required probability? So we train a model, we'll pass all this data set, and based on this data set, the model has to predict the next token, or the model has to assign a probability to the vocabulary so that we can easily predict what will be the next token in the model. So that is the idea. That is what actually a language model. So in short, our probability, our idea is to learn this probability. Our goal is to learn the probability of sequence. There are many ways to represent this, not the probability, but to learn the sequence. The initial models were purely based on the rules. For example, suppose we are building a chatbot, a rule-based chatbot. Say, if the response is say hi, the model has to respond hello. If my response is something how are you, it should respond fine. So that kind of fixed rules they built. Like if you ask some questions like what is the velocity of light, the answer should be velocity, like whatever the question part in the whatever be the question, like the velocity of light is and followed by the answer. So that kind of template we will define, and all the responses will be based on this rules. So these rule-based systems are very well for a small domain, like particularly some domains where we have a fixed set of vocabulary. For example, you are taking a defense domain. Usually in defense, the commandos will like the different troops will send a message to the headquarters using this kind of short messages. So the short messages are very like they have a very definitive rule. They have very limited vocabulary. Using this vocabulary, they will send the messages. Or in some maybe in train and train communication, railway communication, they may like every time they may send some messages to the central networking system. So that kind of messages will be very short, and each code will have a definitive meaning. In that case, this rule-based system will work. But in a natural communication, for example, if you are talking with a customer service center, there may be a different kinds of service requests may come. So all we cannot be put into this template. So many exceptions will come. This rule-based system will not scale based on the evolution of the ecosystem. So people think about a different method. Can we learn this rule inherently by the model? Instead of teaching, instead of saying, defining all the rules separately, can we have a model that can design, that can understand the rule automatically? Then comes the idea of statistical language model, as we discussed in the case of n-gram models. So we will give many examples, and the model will understand this probability. And just based on this probability, the model can predict what next or what could be the output. And statistical language models have a limitation. They were not successful, especially when we have like, first of all, learning this probability is very expensive. We have a large amount of data. From this data, we want to learn all this probability. So training a statistical language model is expensive. And this model cannot work if we have any out of vocabulary words. If a new word comes, the model cannot work because the probability is not there. For example, I have a sentence, I fed the dog. And if the test data contain I fed the cat, it cannot estimate the probability because fed cat is not in the training data, only fed dog is there. They cannot relate that cat and dog have some similarity. They are domestic animals. That kind of similarity they cannot learn. The statistical models cannot learn. They look into the probabilities. They look into the actual count and like the frequency of the model. And sometimes the more frequent words we get a higher frequency. Not sometimes, every time, because probability depends on the frequency, the count. So they will be more frequent than the rare words. So many cases will, like if we are using the statistical model for generation, mostly we'll get the same pattern. So there will be some kind of stereotype. We can easily understand that this is a system generated output. So that is another problem, another issue with respect to the statistical language models. To address these issues, people think about advanced model, which is called statistical language model. So what neural language model. So how we can use a neural network to address this problem? Can we use a neural network to learn these probabilities? So basically we want to define a neural network which will predict the probability of next task. So initially people think about a very common standard neural network that can learn this probability. For example, you can use a feed-forward neural network. So you will give some words as a vocabulary. It will pass through some hidden layers and output for each of the words. So this may be the n to w1 to wn minus 1 words. So based on this probability, the model has to assign a probability of next word. For example, I have 10 words in my vocabulary. My vocabulary size is 10. So I will have 10 neurons in the output. And I will give a sequence as input. So this model will learn the sequence and predict the probability among these 10 words, which can be the next word. What is the probability that W1 will be the next word? W2 will be the next word. Similarly, W10 be the next word. So actually it is computing Wi given some sequence words, like whatever the sequence we need, n-1 words. And what we can compute here is the probability of the next word. And usually we'll take the one which have the maximum probability as the next token. So the word which have the maximum probability will be considered as the prediction. So we will train a model, train a neural network to learn this probability. So we in a training data, what we have is we have the next word. Like actually, suppose W3 is the next word. So we have a, like, let's say for the simplicity, let's say 1, 2, 3. We have only 3 words, and I know that second word is the actual word. So the actual prediction, what we are expecting is 1, 0, 0, 1, 0. And our model will give some predictions like 0.1, 0.8, 0.1. Some prediction it will give. Now, based on this prediction, we actually have to compute. We want to compute the model. We want to compute the next token. Like we have a actual prediction probability distribution. This is what I call it as Y. And we have a predicted probability distribution. And this probability distribution, we can compute the cross entropy loss. So a feed-forward neural network can be used to predict this sequence probability, next word prediction. But this feed-forward neural network has an issue. What is the issue? This R assumes that, like, if you like usually feed-forward neural network will work well with tabular data, structured data. So usually you will have a data set like you have data set like something C. T1, T2, T3, like 3 test results and the corresponding decision. So patient 1, these are the values and this is the disease condition. P2, these are the values and you have some decision. So a tabular data will be the input. So it will have a fixed input size and it will give an output. And this input features are independent. We assume that T1, T2, T3, all this data are independent. And P1, P2 are also independent. Like the patient 1 become a diseased person is independent of whether P2 has disease or not. All the patients, all the features, we assume that independent. But when it comes to language processing, natural language processing, a sequence, the sequence is no longer independent. The next word depends on the previous word. That is the basic idea of any language models. But a feed-forward neural network assumes that all the input, all the features, all the tokens, everything is basically independent. So the sequence dependency cannot be captured by a feed-forward neural network. Also, the input to the model may be of different length. We cannot always say that a sentence will have 5 words. Always it will be 5 words. Or a word will have 5 characters. No, it depends. Sometimes it will be one word itself, one character itself a word. Or 2, 3 words form a sentence. Or sometimes it will be 10 words. So that invariance, that variance cannot be captured by a feed-forward neural network. So these are the limitations when we are using feed-forward neural network as a language model. Also, at every time step, it actually doing a different operation. So every layer, every operation is different. That is also not possible. So to address these issues of feed-forward neural network, people come up with an idea of recurrent neural network, RNN. So what is basically RNN? Let me. So RNN is basically a recurrent neural network. So RNN, what RNN do is, it will instead of considering it as a feed forward or like independent assumption, what it actually do is we have a input function. We'll do it in a different way. So we have a input. So X is my input. and Y is my output. And in between, we have a deep learning hidden layer. So this is my hidden layer. So from input, it will pass to hidden, and from here, it will pass to output. So every time step, it will take one word or one character, one input. So we say this is basically a character, a weight matrix U and V. This is time step one, so X1. Similarly, we'll have one more step. So I can say another hidden. So this is what actually happening in a Y2. This is Y2. So this may be H2. This is X2. So we'll use the same set of parameters here. And we want to make a recurrent connection. So how to connect these two things? So this connection is actually established. The sequence dependency is actually established by taking a connection between the hidden layers of two previous time steps. So mathematically, we can represent it as. So suppose we have a recurrent connection RNN. So the hidden H is basically computed by, like, let's say HI is computed as a function of U into Xi, the current input, plus parameter W into Hi minus 1. So this Hi minus 1 basically capture the previous time step. So H minus 1 actually depends on H minus 2. H minus 2 depends on H minus 3. So inherently it capture all the previous sequences. So H minus 1. So by making this recurrent connection, Hi depends on this H minus 1. All the issues of feed-forward neural network now addressed, because we are each time step we are repeating the same process by sharing all these parameters, and we have a recurrent connection, so sequence dependency is captured. And we will use it for similar, like the same function will be used, like Y will be a function will be a sigmoid tan S or a ReLU, whatever you feel. V Hi plus a bias. Here also you can add a bias term. So this will be the final output of the RNN. So the issues of feed-forward neural network now addressed by the idea of recurrent neural network. I'm just giving a very brief idea of what all these things. But our focus is more on large language models. So this issue is addressed by RNN. At the same time, RNN has an issue. Like you can see that this H minus 1, Hi minus 1, which in turn depends on H minus 2, H minus 3, H minus 4, H0. So suppose you are at 100 times step, it depends on 99, 98, 97 to 0. So the output of 100 time step depends on all the previous 99 time step, which is actually not required. In the previous example, the boy ate apple. The next word is apple. It just depends on the previous word ate. Or suppose you say I was in Spain for long years, and I am fluent with dash. So the next word is Spanish. That is very clear by just looking into the word Spain. So it just depends on Spain, not other words. So all dependency is not required. Because of this huge dependencies, the memory overflow will happen. It will lead to a problem in RNN, which is called either vanishing gradient or exploding gradient. The gradient value during the stochastic gradient descent or the training process, the gradient value may increase, explode, or vanish. Both will be troublesome case. If it is exploding, means it will never comes to the local minima. It will move in a zigzag way. If it is vanishing, means it will be close to 0. The gradient will be close to 0 means the parameter weights will not update. So the gradient descent algorithm will be very, very slow. It will never reach to the proper solution. Both cases are undesirable. And to address this problem, long short-wave memory are introduced. So RNN, the idea is, or LSTM, the idea is, instead of remembering all the information from the previous time steps, it will keep some important information. So it will introduce some gates. So LSTM, the idea is some gates. There are different gates called selective write, selective read, and selective forget. So we'll call it as input gate, output gate, and forget gates. So the original information will go through the different things. So when it go through the gates, it will understand or it will learn which portions are important or which part of the input are important in making the prediction. Only that variable, like valid information will be kept. So who will tell that which is important? Nobody is here to tell which part of the sentence is important. It will be learned by the model itself. So that is the idea of LSTM. And after this LSTM introduction, LSTM was very super powerful model in NLP. From 2012 to 17, you can see many NLP, like most of the NLP application use LSTM and variations of LSTM, like recurrent neural network, by LSTM, GRU, by GRU, CNN plus LSTM, feed-forward neural network plus LSTM. Many combinations, many architectural variants of LSTM you can see in the literature. At the same time, one more problem is getting into interest. So far, we discussed about only sequence learning. At the same time, there are some problems which cannot be just solved by a single LSTM model, which is called seek-to-seek model, where we require basically a seek-to-seek problem. For example, a translation. So in translation, we actually require like input is a sequence and output is also a sequence. So just an LSTM output is not sufficient to identify this kind of seek-to-seek problem. Or, for example, you say take an example of say image captioning. You want to say an image captioning. So you have an image, and output expected is say this is an image. So the boy is eating apple. So some kind of description you want to generate. So how you will generate this one? So the generation, maybe you can do it with a RNN or LSTM. But image, the generation not just depending on the previous word. Usually the language generation, so first word is the, then based on the, it will generate the next token. Then based on the first two token, it will generate the next token. Like that you can generate. But here, the probability of WI depending on what it generates till WI minus 1, also this image. So how you can give this image as a input to the model? So we cannot just give the directly image you cannot give. So we need to encode this image into something like you can use a CNN. So you will give the image to the CNN and this will give a encoded image. And this encoded image can be given to the RNN for generation. So if you see this kind of model, there are two parts. One is called an encoder, and this is basically a decoder. So you have an encoder and a decoder. The image is encoded by a CNN, and an RNN will decode and generate the output. Or even in a translation, the target sentence, input sentence, sorry, the source sentence, input sentence is encoded by an RNN family. RNN means LSTM or anything, and it is decoded into target language by another model. So to address this kind of problem, encoder-decoder architectures become popular. This is called seek-to-seek problem. And in seek-to-seek problem, one important problem is attention. How will you compute the importance of encoder unit? Do you need to cover all the, do you need to refer all the encoded input, or just one particular part of the encoder is important? Let's take one example. I have a sentence. He went to school. This is one sentence. And it's Hindi. I'm not good in Hindi. Say, were school. Yeah, maybe it's wrong, but you assume this is the corresponding Hindi. So if you see a mapping between this input and the corresponding output, so encoder will be, you will encode the sentence and you will get an encoder representation. And based on this encoder, you have to generate the 10 sentence. So first sentence, first time step, you will generate verb. by looking into he went to school. And next time step, we will generate school by looking into he went to school. But it is very clear that an actual translation is not like that. When you are translating, you are not looking into the entire sentence. When the first sentence is generating, we will look into the first word. The more focus will be to the first word he. And the second sentence, school may, school, some word will be there. So it will refer to the two words in this encoder. Or in next sentence, it will look into Gaya, maybe went. So the mapping is different. It is not one-to-one mapping. As you can see, the input have 4 tokens, output have only 2 tokens or 3 tokens. So the mapping is not one-to-one, and the focus is also not in the order. So some kind of mechanism should be there which says that this is the important word at this time step. For example, I will take the same example. He went to school. Well, school. I'm not again. This is not the correct Hindi sentence. For the example, you take this. I'm not good in Hindi. So when it will generate verb, it should focus. Like if you say these are the tokens 1, 2, 3, 4. So verb, it should focus on the first word and all other focus 0. School, it should focus last 2 words. All other focus should be 0. So there will be some kind of vector which say which part of the sentence, which part of the encoder is important at the decoding session. So how to learn this address, this probability or this importance? This is what actually the idea of attention mechanism. So I'm talking about the evolution from a feed-forward neural network to an RNN and LSTM model to an encoder-decoder model, and finally with the encoder-decoder architecture with attention. All these concepts leads to the idea of the foundational model of all the language models, large language models, which is called transformers. So if you understand this background, transformers are basically a deep learning model. As you can see in this architecture, it's an encoder-decoder model. So this part is encoder and this part is decoder, which is basically use idea of parallel processing. So till this point, if you remember the architecture of RNN, it will work time step by time step. Every time step, it will take a word and process it, then predict the next token. So every time step, we look into only one token. But if you see the current architecture, we have a lot of parallel processing GPU access. And in this case, we are using many pre-trained models. The entire input is with us, at least for the encoder. We have all the access to the entire input. All the word embeddings are ready. But still, because of this recurrent connection, we cannot perform this task in parallel. So transformer architecture comes into like the main wish list, main requirement for a transformer model, or the main challenges they address in the paper are: one is we need to process the text in parallel, at least the encoder part. And it should also work with the one is parallel processing. Second one, there should be no sequence dependency. If there is sequence dependency, we cannot work in parallel because Tn-1, Tn depends on Tn-1, Tn-1 by, because all this recurrent dependency, if it is there, we cannot work in parallel. And if we want to work in parallel, there should be no dependency on the order, but the order should be captured somehow. So this model introduced one, parallel processing. Second, the idea of bidirectionality. So instead of looking into one direction, it will capture all the idea in, like, it can take the information from both directions. Like usually the language models, LSTM models, they tries to predict the next token just looking into the previous token. But we know that the word also depends on the tokens which are coming after it. Like both forward and backward direction dependencies are there. So it will capture all these dependencies by a mechanism called self-attention. So if you look into this architecture, you can see that there is no recurrent connection available. So basically, this is a encoder-decoder architecture. So this is the encoder part. This is the decoder part of the transformer. And everywhere, what you have is just feed-forward neural network and some kind of non-linear connections or normalization layers. Other, like if you see the details of self-attention and all, that is just dot products. So dot product is again a linear layers. So you will add some non-linearity and some normalization, that all. So everywhere you can see is just a feed-forward neural network and non-linear connections. Other than that, there is no recurrent connection in the encoder, like the transformer architecture. And this is basically a stacked encoder and stacked decoder. So this is one block of encoder. We have such n boxes, n blocks of encoder and n blocks of decoder. In original paper, there is 6 encoder blocks and 6 decoder blocks. And if you look into the detail, you can see the input will be the text document, and the input size will be very large. We can take entire 512 tokens at once instead of sending tokens one by one. The entire 512 tokens can be taken at once. So a large context can be learned by the model. So the prediction made by the model will be based on a large context, a long context. That is one difference. So input will be passed through an embedding layer, word embedding. Word embedding is nothing but every word, every token will be converted into a word embedding, a vector corresponding to each vector, such a way that similar words will have a similar embedding. Like cat and dog are similar words, so they can have a similar embedding. So word embedding will capture the semantics of the word, the meaning of the word. Along with that, since the word, the inside process is parallel, the word order is not important. To capture the relative importance of the words in the sequence, we'll also add a positional encoding. Like the words in the first position and second position are closer than first and 10th position. So that relative positional importance have to be captured, not the exact position, but is the relative importance of the position. So along with the word embedding, a positional embedding also included. So they combine together, give the encoded word. That will be the input to the transformer. So this positional encoding is usually sinusoidal encoding. I'm not going to the details out of the time limitation. So we are not going inside the positional encoding. It's a sinusoidal encoding, you just assume. So every input embedding, the word embedding and the positional embedding joined together, that will be given as an input to the model. Inside the model encoder block, we have multi-header attention, basically a self-attention. Self-attention, so we see attention in encoder-decoder model. It is very similar to that attention. So this attention is basically attention with respect to the sentence itself. Why it is important, I will tell you. So how important a word with respect to the sentence itself. For example, I have a sentence. So the animal didn't cross the animal didn't cross the road. It was tired. This is one sentence. The second sentence is the animal didn't cross the road. It was congested. So we have two sentences, very same sentence. The animal didn't cross the road. It was tired. Second sentence is the animal didn't cross the road. It was congested. So by looking into the sentence, you can see that in different sentences, the first sentence, it was tired. This it refers to animal. And in the second sentence, it was congested. It refers to the road, because animal cannot be congested and the road cannot be tired. So depending on the words in the sentence, the focus of this particular word will change. So self-attention is a mechanism to capture the relative importance or the focus of a particular word with respect to the other words in the input. So we'll compute the self-attention, and this self-attention is multi-headed. Like suppose we have one attention block, we'll have a consecutive or parallel, say 8 blocks of attention block. It will capture different perspectives of the language dependencies. It will be captured by a multi-headed attention. So I'm not going to the mathematical details of how the attention is captured. That will lead to, we'll get a attention layer, a vector. So from the input, we'll compute the attention, then add a normalizer because like after passing through the attention layer, the values may be in different ways. So we'll normalize it, apply the non-linearity because what we computed is just a dot product, a linear product, linear combination. We'll apply a non-linearity by passing through a feed-forward layer, again normalize it. This will be the output of first encoder block. Then we lead to the next block, where again we will do the same thing. So in the first block, input will be this positional encoding and input embedding. But in the second encoder block, will receive the output of first encoder. That will go in a stack. In the original paper, they have 6 encoder block and 6 decoder block. And finally, we will get the encoder representation from the encoder. Then coming to the decoder, what we have is similar to that. Decoder is basically a language model. It has to generate the next token, the most probable token according to the encoder. So similar to that, we have word embedding. Then the same multi-header embedding is there, but we'll apply some mask because this is decoding stage. All the input, all the expected output is not, we are not interested to unveil. So some part of the input should be, training data should be masked. So we are using a multi-headed, mask multi-headed attention, followed by a cross attention. So between the encoder and decoder, there will be an attention that is called cross attention. And again, feed-forward neural network and normalizer. Every layer we'll add a normalizer to make it normalized. And this output will pass to a linear, like after 6 encoder decoder block, a linear layer will be there. And we have a softmax probability because we want to learn the probability. So the linear layer will be, will have neurons correspond to each of the word, each of the tokens in the vocabulary. And this will predict, will give to a softmax, it will give a probability. So output will be a probability distribution for each of the word. What is the probability that it will be the next token? That probability will be predicted by the model. And this model will be trained over a large corpus, and this probability will be used to predict the token. So transformer as such is basically a pre-trained model. This things will be learned by the model. So LLMs are advanced AI system trained on a vast amount of data. If you understand what is transformer, this transformer lay a foundation for all the large language models. Basically, transformer is a language model. Now, if this language model trains over a large amount of data, it becomes large language models. So a transformer will act as a foundational model. And thus we'll talk about the two important pipelines. Like we can see that there are two things that should happen. So we have a pre-training stage and a fine-tuning stage. So we'll fine-tune. First, we'll pre-train a transformer. So the model here is basically a transformer model. Maybe the number of layers, number of parameters will change, but basic encoder decoder block will be there. And that also depending on what kind of modeling we are trying. So we'll train a transformer model. We'll do the pre-training. Pre-training is basically a semi-supervised or self-supervised learning. Why it is self-supervised? What we have is completely unlabeled data, like all the Wikipedia articles, all the training, all the electronics text available. It is not labeled. We just give the text to the model. From the model, it will learn based on the learning task. It may be a masked language model, can be a conditional language model, can be autoregressive model. Based on the language modeling task, it will learn it automatically. There is no human involvement. So that is a self-supervised learning process. From that, once we have a pre-trained model, we are getting a pre-trained model here. This pre-trained model, we call it as a foundational model or a base model, will give a specific data set according to the task. For example, I want to develop a sentiment analyzer. So I will give a sentiment analysis data set, very fine-tuned data set, very precise, narrow data set to the model and update the parameters. So we'll fine-tune this. Fine-tuning means we are updating the model parameters. During pre-training, all the models, all the parameters will be trained to a certain values. These values will be adjusted according to the task. We'll get a fine-tuned model. Once we got a fine-tuned model, we may apply the technique called prompting. So this large language models are now capable of understanding the instructions via prompt. Prompt are the instructions in natural language given to the model. So we will give some indirect or direct prompt. For example, I will say your responses should be of this type. This cannot be, you should not respond this kind of questions. So or respond like you're asking to like a expert in physics and physical engineering. You are like a machine learning data scientist. You want to respond. So you will give all the roles, all the tone, what kind of response, what kind of the level of language, what kind of language they have to use, whether it is for a kid, whether it's for a school student or a graduate or for a scientist. So depending on that, all that indirect tuning will be done on the fine-tuned model. Finally, we'll get a learned model, and this will be used for different large language model applications. So this is a flow, what is happening, and the key part here is transformer that we learned just. The other part is we train a transformer model, apply on fine-tune for a particular application, and do the things. And when it comes to the transformer or large language model taxonomy, the transformer, this is the encoder part and this is the decoder part. There are two major families or three families we can say. One is encoder only models. We call it as BERT family models. BERT, Albert, Robert, many models are there. This is basically working on the encoding ability of the transformer. So what is encoding? It is basically representation learning. Given a text, how we can represent this data in a better model. We have word embedding, which is a vector representation of a word. So word embedding is a static embedding. Like every word, irrespective of the context, we will get a representation. A more context-aware representation can be learned by BERT models. Why? Because this encoder, transformer encoder, have a longer context window. The original paper, the transformer architecture, the window size is 512. So 512 words, around one page or 2 pages of 500 words means we have around 2-3 pages we can give as a context. So the word embedding, the vector representation will be learned from this much longer context. So that will be more dynamic, more context aware embedding representation will be good. So the BERT model will be focusing on the abstract representation or abstracting of the input data. On the other hand, decoders, the GPT family models, will focus more on the generation part, decoding part. So without the decoder, it will focus, without the encoder, it will focus on the decoder part. So how basically the language model task, given a sequence, how it can generate the response. So most Gen AI applications comes in this side, how to use GPT or GPT related models for generating the data. And sometimes we'll talk about encoder decoder model. For example, T5 model or PALM model from Google. This belongs to both encoder and decoder. Basically used for sequence to sequence learning tasks. For example, translation. It requires both encoder and decoder. So T5 model can be used for this kind of encoder decoder task. So majorly 3 classes, but we focus more on the 2 classes. One is encoder only models and decoder only models. So most of the large language model application comes in these two classes. One is representation, encoder only model. The other one is generation, decoder or GPT based model. So a representative example from encoder only model is BERT, bidirectional encoder representation from transformer, again from Google. So BERT is built entirely on transformers encoder part. So it's just encoder, but it will increase the number of layers. Instead of 6 in the original encoder block, in the original transformer purpose, there will be 12 to 24 layers in the BERT model. So as opposed to the unidirectional model, again, this is bidirectional. We'll take both left to right and right to left. And transformer encoder is the entire sequence of the word at once. Instead of learning, like if you remember RNN, it will learn word by word, token by token. Here it will learn it from the complete text. Input sequence will be learned, reads completely. So it is bidirectional model. So these are the basic steps happening in BERT. We'll have a pre-training step. We'll train the model over or the large corpus like Wikipedia articles and all the English textbook, whatever it is. Then we'll train the model on different tasks. There are two important tasks. One is mask language model and the other one is next sentence prediction. So on these two tasks, the BERT model will be trained and we will get a pre-trained model. Now, this pre-trained model will be fine-tuned for a particular task. For example, we want to do a email spam classification. So this will be a particular data set. A very small data set is required. Using this data set, we'll fine-tune a pre-trained model. So pre-trained model is already trained to predict this mask language model, mask language model, or next sentence prediction. In that way, the model is already learned. Based on that, we will fine tune the model to predict or classify the text into spam or not spam. So we'll get a fine tuned language model. So pre-training the model, so a foundational model that will be fine tuned for different models. For example, a BERT model for question answering, a BERT model for named entity recognition, a BERT model for uh, natural language interface. So for different things, we'll have a different BERT model. You may heard about different BERT models like Indic BERT, Fin BERT, RNA BERT, protein BERT, DNA BERT. So if we train the model on different things, fine tune a model for different tasks, it become a different BERT models. That is the idea of BERT pre-training. And you may heard about different models in the BERT family. One is Albert, like BERT is proposed by Google. Then to improve the or gap in the BERT, many other architectures were proposed. What is Albert, a light BERT, which is lighter version of the BERT with lesser training time. Roberta is basically an OpenAI model that is robustly optimized BERT pre-training approach. Electra is another model. Span BERT, distilled BERT is a distilled version of BERT. Like we'll do a knowledge distillation to make it lighter model. And tiny BERT, again similar to digital BERT. And domain specific BERTs are there. You can see more details from the link below. I will share this link. So one class is encoder only models, basically focusing on the representation learning. The other part is generative pre-trained model, the popular GPT. So Open AI proposed this GPT and various versions. Currently, I think GPT-5 and higher versions are running. So GPT is basically a decoder only model focusing on the auto-regressive language model. That is, it is predicting the next token. So auto-regressive modeling or causal language model means based on the previous token, it will predict the next token. So as you can see in this architecture, this is the transformer block, the decoder block. It will predict the output. Like in the basically there will be a probability layer that will predict the output probability, and based on that, it will predict the next token. The difference from a transformer decoder is that in transformer, decoder have two types of attention. One is mask attention, the other one is cross attention. That cross attention is not relevant here because there is no encoder block. So this have only mask attention. That is the only difference. Otherwise, it is very similar to the decoder of a transformer. I hope you are following and there is no query in between. So focusing on the generative part of the language modeling, that is what actually the GPT is doing. LLM continue to generating the text token, next token, condition on the prompt. So here, instead of like it is not just depending on what it generated previously, it produce it output based on two cases. One is prompt, and also the output it generated in the previous times. And to make this production, this generation more natural, we know that they are not always saying the same words. Sometimes we'll use some synonymous words to represent the same context. Like we are not repeating the same word. To make it more natural, more humanized, instead of predicting the most probable one, the GPT architecture will follow some decoding technique. So one such approach is there are three decoding strategies. One is called uh, 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 greedy approach. Like every step time step, it will focus the one which have the maximum probability. So decoding can be done. One is greedy approach, where every time step it will go to the most probable one, or it can go to the exhaustive search. So it will check all possibilities. Out of all possibilities, it will predict the most probable sequence. And the most popular in between is beam search. So instead of going for all the possibilities, it will take some top K possibilities and compute the most probable one. So it is not greedy, not exhaustive in between. It will pick some top K. So this kind of three decoding strategies will be used in a decoder. Also, it is not the most probable one. It will go for some top K sampling, like random sampling. Out of the top probabilities, it will randomly choose one. So suppose I'm looking for top 10 words. Out of 10, the next word will be chosen randomly out of this 10 words, not always the most probable one. Why? Because if we are just going for most probable one, everything will be definitive. So we are using LLM for creative writing. If the output response is always definitive, like well defined, predictive, that means it is not creative. We are looking for a diverse output. If we give the same prompt at different time step or by different users, we'll get different responses. So this is because the model follows a top K or temperature based sampling. These are two important parameters in GPT models that will address the diversity of the generative model. Why this is important for this kind of language modeling is important. So the person will answer most likely like what we are teaching, the training the model is on a language modeling task, predicting the next task. If the model can predict the next word correctly, like it can understand that means that it is a strong indication that it understands the language properties very well. For example, in this example, you can see you have a sentence like wow, India has now reached the moon, and you are asking a person what is the whether this sentence is positive or negative. So if a person knows the language, he can say, even though he is not trained on a sentiment analysis task, he know whether it is a positive sentence or negative sentence. Or given a sentence, you can, if you ask some questions, he can easily ask because he know that. And some of the sentence which is meaningful and meaningless, if he trained on the language, he can answer. He or she can answer. He may not explicitly trained on all this tasks, but if he know the language correctly, he can answer all these questions because linguistic understanding, a language understanding is required, not the entire task specific training. So that is a key idea in GPT models. We are training the model to predict the next token correctly. If the model can predict it correctly, that give a clear understanding, clear indication that the model learns language very well. And based on that understanding, it can predict the next tokens properly. So that is why all the tasks can be represented as a language learning task. Now we talked about LLMs and transformers. The next task is to bridge them. LLM with transformers. So language modeling is the task of predicting next token in the sequence. And we will train a transformer model to predict this token. So this autoregressive model or a conditional probability model that will assign the probabilities given and will the parameter function with a fixed number of parameters. So this model will learn this kind of conditional probability. And we give the LLM an input piece of text. Generally, we call it as prompt. So the response from the LLM will be conditioned on prompt because transformer is learned to predict the next token based on the input query. So here we are training the model to generate the response based on the prompt. So the condition we are providing here is prompt. And many practical NLP tasks, if you see, can be represented as a word prediction task. For example, sentiment analysis. You have a sentence like, I like Jackie Chan, and the expected output is positive or negative. So which can be taken as a language modeling task. Like what is the probability that positive as the next word given the sentiment of the sentence I like Jackie Chan is. So given this sentence, what is the probability that positive will come as the next token or negative will come as the next token? So sentiment analysis basically a text classification expecting a label as an output, which can be converted into a language modeling task, a word prediction task. Or question answering. Who wrote the book Origin of Species? And you are expecting an answer A. So you can convert into the next token. You want to predict the next token W, given the sentence, the question, who wrote the book, The Origin of Species. And suppose the first token generated is Charles. Given this Charles, what could be the next word? Origin of species, Charles. So next may be Darwin. So in that way, any task we can convert into a language modeling task, as you can see here in the case of text classification. So what we discussed so far is the language model, how this language model can be done with traditional rule-based, statistical, neural language model, and how it reaches to the transformer architecture. Then in transformer, we discussed about encoder-only models and decoder-only models, BERT and GPT. And we saw that any of these NLP tasks can be represented as a language modeling task. So all this give a very brief introduction to large language models. And we are very much aware of the power of the language model as well as the risk associated with it. So next few slides, we will see how we can use a large language models for different applications. For example, we are using language models, LLMs, maybe ChatGPT, Gemini, or related models, directly some models, or the applications like GPT, Gemini, or Claude, Perplexity, many other models. We are using for different functions. For example, content generation we can use. They are giving unique responses. Or we can use it for information retrieval. So we can give some queries directly to ChatGPT. They can extract the answer. Or given a PDF, we can ask some questions. So this can be extracted from the extracted by these models. We can use it for language translation, obviously. We are using it for text summarization or given a paper, the entire summary we can generate. Writing assistant, we can improve the sentence, we can polish it, or we can check the grammar, we can change the tone, anything we can do. Or as a conversational agents, we can talk with them. We can do a brainstorming session with AI models. They will give ideas. We can take it or we can reject. We can refine our ideas. So mostly we all do this kind of things. So let's show a very quick demo on how transformer models can be used for multiple functions. So in case if you have any query. Okay. So I have a quick demo on how the transformer models can run. I hope my screen is visible, right?
Sir, visible, sir.
Yeah. So this is an example where we are using a transformer available in Hugging Face for different purposes. I'm not doing any kind of training. I'm just using some of the models available in Hugging Face to do some tasks. If you are already familiar with some of the NLP tasks like sentiment analysis, how difficult it is to create a model or what are the training, what are the steps to be done, you can understand the difference. So in the first example, I am just taking a pipeline. So Hugging Face pipelines are a standard set of operations that are used to. Is there any query? I hope it is not a query. Uh, Hello, sir. No, it's not a query, right? Yeah. So,
Sir, there is one question in the chat box, sir, from Mr. Kumar.
okay, fine. No, but I couldn't see the question.
Can I read out, sir?
Yeah, sure.
Sir, can you please specify the types of transformers used in medical image processing? How transformer are connected to CNN model? That was the question.
Okay. So, I have limited experience in image processing, but there are vision transformers available that are pre-trained models. Now, like it's not completely CNN based, but transformer based models are available. So vision transformers will be helpful for all this kind of image processing tasks. So a transformer architecture trained on images, we can simply say that. And the second part of the question is how it is connected to CNN. We can connect in different, yeah. Yes, sir.
Actually,
Kumar.
myself, Prashant Kumar, I'm the faculty of GKT, Srikakulam Triple IT. So I have gone through your entire session. It was good. So it's just like a repeated session where I have complete my AAML applied AAML PG degree. In that, I have aware of all this kind of lecture. It's very good, and I have already experience with NLP also. Sir, basically, my question is to that transformer. You're talking about encoders and the transformers. So basically, how transformers are basically working or generating model, because I'm not clear about that.
Okay. So transformer are basically, if you remember the architecture that I shown, it is basically a neural network model. So here you can see the architecture. It is basically a neural network model. So what we are giving as an input to the model is a vector. So basically the text will be given into some label encoder. That will be input. Input encoder is basically convert every word into a vector. Positional encoding also will capture the positional information as a vector. And the key part is within this block, headed attention, multi-headed attention, or basically a self-attention and a feed-forward neural network connection. So
And
they are
GAN
trained
also
to
doing
predict.
same work now, sir. GAN also doing the same work now.
GAN, the main difference is that GAN is a generative model. It is trying to like the training process is different. Here the training is auto-regressive model, like it will predict or a kind of mass language modeling. It's similar, but the architecture wise, we can see some differences. Like self-attention is not there in GAN. That is a key part in transformer architecture. And if you take the encoder architecture, the BERT model, the learning task is basically mask language modeling. This is specific to BERT family. Like we are applying some mask inside the text data and ask the model to predict that mask masked word. So if the model can predict the masked word correctly, we can say that the model learns, the parameters learns well. So GAN is also a generative model. Like there are different way of generation. Like autoencoder is a way of generative models. GAN is another way of generative models. Transformer is also a generative model. It is conditional language model, like conditionally generating the based on the sequence, these probabilities will be generated. If you take autoencoder, it is kind of reconstructive error. It will compute the reconstruction. So autoencoder models are trained over reconstructive loss. Or if you take GANs, that there will be a different learning function, training function. Transformer have a different training function. So, and the number of parameters in the model is very large compared to GAN or autoencoder models. So transformer is very large in size of parameters and in large in size of training data also. And the other two models are not in parallel. We can do the process in parallel here. That are the clear differences between these two models. Hope it is. Hope I answer your questions partially at least.
Yes, sir. Yeah, yes, sir. Yes, sir. So basically, I have a big question about generator, the GANs and transformers because I'm working on transformers. So that's the reason. That's it.
Okay,
Basically.
good. Yes. Yeah. So I will have a quick demo. You can see a sentiment analysis. I'm just calling a pipeline of sentiment analysis and give a sentence to do the classification. I'm not doing any kind of training. This is a pre-trained sentiment analysis available, and you can see the description. This is from Distilbert, base and case. So this is basically a base model for English trained for sentiment analysis, and you are getting a score, say, as a positive sentence with confidence of 0.95. And if you see a question like the script of the movie is impressive, though the casting is poor. So the script of the movie is impressive, though the cast is poor. So the movie is somewhat negative, more negative than positive. So you can see the score here is 0.81. It's a negative with 0.81. It is not completely negative. Some positive words are there. So the score is reduced. Otherwise, it will be very high score. Like you can see that I have been waiting for Hugging Face course. I hate this so much. So I hate this so much is completely negative. So it give a very high score of 0.999. And as the movie is not watchable, you will get a very high negative score. But movie was watchable, though the story is lagging. So it's okay kind of feeling. So you will get a small negative or a lesser negative score. So what I mean is the model is learning all the sentiments. We are not doing any heavy training. By just calling the function a pre-trained model is already learned. This sentence anyway, it is not in the this is the new sentence I'm giving. It is not in the any training data. Or more interesting thing is here, say a zero-shot classifier. I'm using a transformer model. Again, this is BART model, from Facebook. We are using a zero-shot classification. So zero-shot classification means we just give an example and ask the model to do the classification. So the task here is I give a sentence. This course is about transformer library. And the labels I want to predict are education, politics, and business. So usually a text classification, we need a data set where each sentence and the corresponding class label will be there. The model will be trained on this label data set. But here, I'm just following a zero-shot approach. I just give a sentence and ask the model to predict. And the output, you can see that the sentence, education, it's assigned a score of 0.84. Business, it assigns a score of 0.11, and politics, it assigns a score of 0.4. So even without talking about this model or this data in detail, the sentence is new, the class labels are new, the models are not at all trained on this sentences, this domain. It gives a very good answer, very correct answers. And so many examples are here. I'm not going to all these examples. You can see how efficiently generate the the sentiment or the text generation. For example, in this sentence, say I just give Dr. Reddy is a computer scientist and ask to generate the sentence. So Dr. Reddy is a computer scientist at the University of somewhere, where he working on some of data science foundation or the 30 books, some generate content he generated. Or this course is about mathematical model. So many things we can generate. This example I will share. I'm not going like it's already 7:25. I'm not going into detail. So the idea is that the models, the pre-trained models are so powerful. It can understand the language very well and work on the output in a best manner. What we discussed is the power of transformers. At the same time, you know there are many limitations also. For example, the model are very known to hallucinating the content, non-factual output may come, or there are many ethical considerations, and there are also many issues related to the social cultural output. As you already see in ChatGPT, it can make multiple mistakes. So there are a lot of limitations in connection with this model. So LLMs can do many things at the same time. As an early stage technology, we cannot say now it is early stage, but it is still not matured at least. It's evolving the capabilities and users create potential of manipulation also. Like many AI videos are now coming. So how much believe the new content? There, like a lot of people are misusing this content. Like even ChatGPT, we can just generate a research paper from using this AI models. So how ethically correct it is. And there are many unintended or unforeseen consequences. Like people may not think about this consequence when this model is used in the things. There are many cases, you know. For example, Google Gemini's recent news, you may be noticed. Like a student asked Google Gemini many things, and finally the model responds that you are waste of time, a burden to the society, go and die. So this kind of responses will is not expected from an AI model. Or there is another news happened, like airline model, airline company followed a LLM based chatbot. So chatbot make a mistake. Because of that, the traveler lost his flight and make many like financial problem happen, loss happen. So when case like when he approached the court, the company says it is not their mistake. It is made. The mistake is made by the chatbot. So there will be an important question: if an LLM model or a AI model make a mistake, who owns the responsibility? Whether it is the responsibility of the company, like the airline company, or whether it is a responsibility of who made this LLM, like OpenAI or Google or whatever the LLM you are using, or whether it is a problem of the person who used the LLM, like use the ChatGPT. Anyway, the court says this company has a responsibility. So this will create a problem, like who is actually responsible for the response coming from this AI models. And there are many edge cases you can see, and model hallucinate out of the grounding information. What quality of data they are generating? Like the models are trained over the data over the internet, and nowadays mostly this blogs and many news are generated by AI models. So model is training on their own data. So the naturality, human like the natural things will lost in the training. So this become a challenge, and there may be some bias. And trained over a biased data, this bias will get amplified. The quality of the language we cannot assure. We may sometimes will like our students will give a very quality result, and sometimes it may be original, or most time it may be from an AI model. The models has no domain expertise, even though we are thinking of talking about RAG and many other knowledge graph based additions. Still, they lack domain expertise. So, in critical areas like defense or say medical domain, how we can deploy it, and many examples you can see is for the main thing is a bias problem in the model. For example, my friend is this very popular example. If you use an AI model to translate this, my friend is a doctor and my friend is a nurse. In both cases, the structure is very similar, and the output generated in Hindi, the language like where the gender is important, you are getting a different output. Mera dost ek doctor hai or meri dost ek nurse hai. So even this seems to be linguistically correct, like grammatically correct. Like the behind the screen, there are a lot of bias issues are there. Like we never mentioned my friend is whether it is he's a male or female, and my nurse is also not. I haven't disclosed whether it is male or female, but without any clue, the model decided a doctor is masculine and nurse is a Mary, like gender is female. So this is the kind of bias in the model. Similar bias you can see in your Meta AI model also. It is not just Google Translator. Most of these models have this issue. If I just ask in the WhatsApp Meta AI, I ask to generate an image of an Indian actor, Indian doctor. It generates something like this. Very good. It's not a bad image. Like typically it's a doctor, like he has stethoscope, white coat, and you can see some ECG and ventilator or ICU background. It is okay, you can understand it's a doctor. But how you can say this is the Indian doctor? Or how you can say this image is a Indian representation? On what basis you can see? Based on the color? We have many other colors also, like we cannot discriminate or distinguish one country by the color. Or if I say generate an image of Indian more generally, it gives a image like this. But there are many other Indians also. Like anyway, many people I know which is different from this person, and how I can say he's an Indian. So the models are very much biased. So this bias will create a lot of problem when you are using, like now this AI is not so far from us. It is very close to a common person. Like it is available in mobile phones when we are reading news, when we are even driving, everywhere it is there. So it is very close to us. So this kind of bias may not be like in a peripheral sense, it may not be that much problem, but it will create a lot of disparity, a digital divide between those who have and those who have not access. For example, most of the models working well with English. So that facilities, for example, you want to create a resume in English very quickly using ChatGPT. But can we do the same in Malayalam or Telugu using this model? So there is a digital barrier. Those who know English, those who know all this technology can access all these things. Others will be away from this technology. So this LLM model is also creating a digital divide. So this problem is there. A kind of stereotypical belief will be propagated. We want to like this will create a different problems. Most importantly, the people will lose faith in the model, and it will also increase the digital discrimination among the society. So we need an explainable model, and all this criteria like robustness, safety measures are required to, like when we are implementing a model. I'm not going in detail. So to utilize this technology safely, as we already discussed, there are a lot of power coming with LLM, and if we go beyond LLMs to agents, like now this is the era of agents. The next technology is agents after LLM or along with LLM. LLMs with multiple tools. Now it become more powerful agents. So when using this kind of technology, at the same time, we want to consider the risk specific to your use cases. majorly this kind of social issues. It should not create discrimination. It may solve your problem. At the same time, it should not create any kind of unfactual or biased responses to the from the model. So make sure that your model follows all this kind of safety filters as required. Or the most importantly, it should include human in the loop. Like whenever we talk about the process, most cases it is model all itself learn the things. It is semi-supervised. We give the data, model learns the parameter, model adjusts the parameter, model predicts the output. So this pipeline should be redefined with human in loop. Human feedback should be involved. Now, if you see the ChatGPT response, sometimes it will give two responses, which you prefer, response one and response two. So that is a kind of feedback there the model is learning. So based on that kind of human in loop way, this model can be better. The power can be used in a better way, and all the limitation what we discussed can be mitigated. So that should be the motivation. That should be the way how we have to use LLM. So the final word what we use here is NLP to LLM, the traditional NLP to the current large language model, an extraordinary evolution in our quest to understand and interact with human language. We can see the progress, like every day it is getting improved. Lastly, from 2010 to 2020, if you see the improvement, it was yearly or biannually we are getting a new models. But after the chat GPT or maybe from 2022 onward, you can see every day it is getting improved. So the models are learning the language so fast. So many miracles can happen. So this is an extraordinary area where you have a lot to contribute, both technically, socially, philosophically. Many things you can contribute, and you can understand it in a wide range. So, and those who are very new to this area, I have some suggestions to start with. If you want to learn in depth architecture, as Kumar sir asked, I want to know how the transformer model is training. So I suggest a course by Mitesh Kapra. This is offered by AI for Bharat. Initially, it was an AI for Bharat platform. Now it is available as a YouTube playlist. You can just search for Introduction to LLM. Or there is an NPTEL course by Tanmay Chakravarti from IIT Delhi about Introduction to LLM. He's recently won ACM India Outstanding Contributor Award. Another resources, LLM University by J. Almer. He also wrote a book on hands-on large language model. If you go to Hugging Face, one of the important repository for LLM, many data sets, models are available in Hugging Face. They also provide an NLP course which talk about all how to use this LLM models in different ways. Deeplearning.ai, along with Coursera, they offer many courses. Now Google also offering this kind of courses, certification courses, small modules. To get a very peripheral idea, this courses may be helpful. But if you want in-depth research level understanding, I suggest to go to either Introduction to LLM by AI for Bharat or Tanmay Chakravarti course. And most importantly, you have to start experimenting with small LLMs, models available in all these things. So with that, let me conclude the session. What we discussed is what is large language models focusing on transformer and a general overview of different technology. We discussed the power and limitations in a brief manner. So this is very brief introduction, not in-depth lecture on any of the topics, but a very peripheral introduction to all this evolving technology. Thank you for listening. And if you have any question, I'm happy to take it up.
Yes. Thank you, sir. Dear participants, if you have any question, please raise your hand so that I can give a mic access. Dear participants, if you have any question, please raise your hand. I can give mic access. Otherwise, we can wind up the session. Or you can post your questions in the chat box so that I can inform to resource person. You can post your questions in the chat box also. So no questions, sir.
Yeah, thank you. Thank you all
Sir,
for listening. Have a nice day.
Yes, sir. I would
And
like
a
to
wonderful
extend
activity.
my sincere gratitude to you, sir, for your
Thank
insight
you.
and
Thank you.
informative session on all the neural language models, sequence learning problems, probability, on calculating how to calculate the probability of a sentence, Ngram models. The risk also you informed, sir, along with Hugging Faces demo. I would like to thank all the participants for your active participation and engagement in the today's session. We will share the feedback link in the WhatsApp group. We are sharing in shortly. So once again, thank you all for being part of today's session. Thank you, Manu Madhavan, sir.
Thank you. Thank you all.
Thank you so
Have a
much.
nice day.
Yes.
Thank
Thank you
you.
so much.